Okay, now let's continue with another example. As we see from the screen, we have truss elements. This is K1, this is K2, and we have K3 here. And K1 and K2 is connected to a rigid wall with node 1. There is a rigid block which connects the three elements 1, 2, and 3. In fact, there acts a force of 5 Newton, we can say, and K3 is also connected to a rigid wall at node 2. So the numbering is given like this, so 1, 2, and 3. Okay, so let's write the element stiffness matrix first, K1. So it is symmetric. The diagonal terms are positive and off diagonal terms are negative. So it is K1 minus K1 minus K1 and K1. Certainly node 1 of element 1 is the node 1 in the global system. As you see, this is this node, and node 2 of the element 1 is node 3 in the global system. Therefore this is 1 3 and 1 3. Now let's look at the K2, the stiffness matrix of element 2. Now this is element 2, as you see. Again, its stiffness might be different. Okay, so this is K2 minus K2 minus K2 and K2. Of course, node 1 of element 2 is node 1 in the global system. Node 2 of element 2 is node 3 in the global system. Identically, node 1 and node 3. So this is 1 3 and this is 1 3. Okay, let's look at the K3 now. Element 3, and write its stiffness matrix. So certainly node 1 of element 3 is node 3 in the global system. So this is node 1 of element 3. Now focus on node 2. Node 2 of element 3 is node 2 in the global system. As a result, so this column is associated with the node 3 in the global system, and this column is associated with the node 2 in the global system. Identically, this is associated with the node 3, this row, and this row is associated with the node 2. So this is 3 2 and 3 2. Okay, now let's sum up the values. So how we are going to do is, first we will sum up the values from 1 1. So we have 1 1. Okay, so it is K1. Let's look at the other one, second element. Do we have 1 1? Yes, it is K2. So K1 and K2 is sum. Now do we have 1 1? No, we don't have it, because we have nodes 3 and node 2 in the element 3. So this term is K1 plus K2. Okay, let's continue. Let's look at the 1 2. Do we have any nodes 1 2 in the rows and in the in the rows and in the columns? No. So this is 1 1, this is 1 3. Let's look at this stiffness matrix. So again, identically, this is 1 1 and this is 1 3. Let's focus on this one. Again, this is 3 3, this is 3 2. So as a result, 1 2 is 0. We don't have any value for 1 2. Now let's continue. Let's look at the value for the 1 3. This is the 1 3. So we have 1 3, sorry, yeah, for the 1 3 we have minus k1, or you can think like this. This is 1 and this is 3. First row and third column, 1 3, it is minus k. Let's look at the 1 3. This is 1 and this is 3. It is minus k2. Do we have 1 3 or 3 1? No, we don't have it. So it is minus k1 plus minus k2. So the 1 3 is minus k1 plus minus k2 as a result. Okay, so we completed the calculation of the first row. This is another way of solving the problem. Okay, let's continue now. So let's look at the 3, not 3. Now 3 1, we have minus k1. For 3 1, because this is 3 and this is 1, minus k2, minus k1 plus minus k2. Do we have 3 1 here? No, we don't have it. So it is minus k1 minus k2. Now let's continue for the third row again. So 3 3. Okay, we have k1. 3 3, we have k2. 3 3, we have k3. You see? So as a result, we have k1 plus k2 plus k3. So it is k1 plus k2 plus k3, because these are the nodes 3 3. Values associated with the node 3. Okay, so let's continue further. Let's see here. We have here 3 2. Okay, and 3 2 is minus k3, and as a result the third row in the second column, the element will be minus k3 as a result. Now let's focus on the 2. Now when we look at the 2, we only have nodes values associated with node 2 in k3. We don't have any value associated with node 2 in elements 1 and in elements 2. Therefore we will focus on 2. First thing is node 2 is associated directly with the second row. That's okay. And we have 2 3, because this is 3 and this is 2. 2 3 is minus k3. Okay, you see, this is the second row and this is 3. Okay, and 2 2 is k3. As a result, 2 2 is k3. Now we form the global stiffness matrix by directly summing up the proper nodal values inside the element stiffness matrices. This is another way of doing this operation instead of using gather and scatter matrices. Okay, now we will form the global nodal displacements. Of course, value at node 1 and node 2 is 0. It's fixed to the wall. Okay. We have only free node at node 3. That's also okay. Let's look at the external forces. So external forces are 0 for node 1 and node 2, but it's 5 for node 3. We have value of 5 here, you see. Now let's look at the reaction forces R. It is R1 and R2 at node 1 and node 2. So these are the values. Okay, now we have the stiffness matrices and we need to associate the essential and free nodes. So remember that the free nodes are the nodes in which we don't know the displacement, and we have the essential nodes. Now this is our global stiffness matrix, this is our global displacement vector, and this is our force vector in the global system. Now how we will decompose it? Certainly we have the Kf. Okay, so this is our Kf now. You see, K1 plus K2 plus K3, and this is our Ke, the matrix associated with the essential nodes. Stiffness submatrix of which is associated with the essential nodes. So it is K1 plus K2, it is 0, 0 and K3. Now we have the Kef, it is minus K1 minus K2 and minus K3 in the second row, and we have the transpose of it on the other side. Look, again the global stiffness matrix is symmetric. Now certainly we have the essential nodes as reaction forces associated with the essential nodes, and we have, you see, the force vector associated with the free nodes. Okay, now as a result, this is our system of equations. Now we need to solve it. In fact, we don't know the displacements df, we know the displacements de, but we don't know the Kef. We know the Kef, but we don't know the reaction forces at essential nodes. So when we decompose it, what we have is the essential stiffness matrix, the submatrix of the global stiffness matrix associated with the essential nodes here as Ke. This matrix is associated with the essential nodes. This is associated with the free nodes, and we have the matrix which couples the essential nodes with the free nodes. Okay, we have the displacements in the essential nodes also. We know the values. We don't know U3. We know the force FF, and we don't know the reaction forces RE. So if we make this multiplication, so Kef multiplied by the Kf, and take this row and multiply it with this vector, so it is Kef multiplied by De, Kf multiplied by Df. Now Kef transpose multiplied by De is automatically 0. Okay, so because the values here are 0, and taking the transpose of this matrix, okay, and multiply it with this one will give us 0, and from here what we find is K1 plus K2 plus K3 multiplied by U3 is equal to 5. From here we can easily find the value for U3. Okay, so 5 divided by K1 plus K2 plus K3. So whatever the stiffnesses of the members are. So once you find the U3, you can easily find the reaction forces, because now you will take this first line of this system. Okay, now you have calculated the df. What you are going to do is you will multiply the Kef with df, right? So it is Kef multiplied by U3, and now you know the de. As a result, Re is equal to Kef multiplied by U3. Actually, it is minus K1 minus K2 multiplied by 5 divided by K1 plus K2 plus K3 for R1, and for R3 it is minus 5 K3 divided by K1 plus K2 plus K3. Okay, we may have other linear systems, of course. So this is not, the truss elements are not the only ones. In fact, you can use such kind of a solution methodology for solving other linear systems. So what are those linear systems? What might be? In fact, you may have a current. Okay, here at node 1 it is I1. You may have the potential there, E1. Okay, so the voltage. RE is the resistance now. Because you have a resistance, you may have circuit here. Then you have node 1 and node 2. And of course, you have E3 and I2, E2 and I2 at node 2. So you can write the Ohm's law in this case. So E2 is nothing more than the difference in the potential. Okay, so this is the voltage, E2 minus E1 divided by the resistance. This will give me the current, or the number of electrons per unit area that flows at point 2. So this is how you can calculate the current. Identically, you can calculate the current at point 1, and of course the sum of the currents entering to the wire from left and right has to be equal to 0. So it's like this. So therefore the current is analogous to the force in our case, and potential at point 1 and 2 are analogous to the displacement, and R is analogous to the stiffness. So we can write, or 1 over R is analogous to the stiffness, sorry. So we can write the relationship between the voltages and currents, as is the case in here. Okay, so E1, E2, this is analogous. We can say that this is F, so force vector, and then we have the element stiffness matrix here, and then we have the element displacement matrix. Certainly, of course, you can use gather and scatter matrices. Therefore, you can write LE multiplied by D in order to gather the global potential values at the nodes to the element by using this operation. Of course, this is not the only case. You can use such a system in order to calculate the fluxes, volumetric fluxes or mass fluxes and pressures in a pipe network, for example. Certainly in a segment of a pipe, the net flux entering to the pipe and from both sides has to be 0. Okay, so this is one expression that we use. You can think like this. So the flux, it can be the volume flux or mass flux. So the flux, sum of the fluxes has to be equal to 0. The second thing is the pressure difference, okay, at P1 and P2 will generate a flux. In this case, the fluxes are analogous to the force and the pressures are analogous to the displacements. Okay, So we may have much more complicated systems. Of course, in this case, numbering might be important. Now, for example, we have a linear truss system here. So this is my node 1, this is my node 2. So I just give number to the essential nodes one by one. It can be either at the top of my vector or at the bottom of my vector, doesn't matter. So here, for example, let's count the number of nodes. I have 1, 2, 3 and 4 nodes. Therefore, first two nodes can be the essential nodes, or the last two nodes can be the essential nodes. So grouping them makes the things rather easy. Therefore, you can easily calculate or decompose the matrix. Okay, we may have some other systems. Of course, as you see, you may have a pipe network. For example, here is an example of a pipe network. This is my node 1 and this is my node 2 because this is at the boundary, and certainly the pressure at the boundary is given, the displacement is known here, and then you can calculate it by establishing the proper stiffness matrix. Now here we have a circuit. The potential at node 2 is given and potential at node 1 is given. It is 0 here and it is 10 R1 here. So R1 is here, R3, this is R3, the resistance 2, resistance 1, resistance 3, resistance 4 and resistance 5, and this is resistance 2. So we just give the numbers properly. This is my first node, this is my second node, then I give a node here, this is node 3, this is node 4. In fact, you can, well, there is no resistance, so you don't need to put another node here. Okay, now how about the two-dimensional systems? Now, two-dimensional systems are not that different than the one-dimensional systems, in fact. But in this case, when we have a truss system, certainly your truss element makes an angle with one of the axes. For example, here it makes an angle with the x-axis, and certainly it has a stiffness again, Ke. And this stiffness controls its deformation along its direction. But in this case, the number of forces and displacements associated with the nodes are different. So let's look at the node 1 of an element. So in this case, I have u1x, as you see, and f1x. F1x is the force in x direction and u1x is the displacement in x direction. Then the next thing is I have force 1y, F1y and u1y here. So these are the force and displacement in y direction. It is the same for node 2, as you see. So it is the same. In fact, I have a force and displacement component in x direction and I have a force and displacement component in y direction, as you see. Okay, so it's not that different. In fact, just assume that I have a coordinate system which is linked to the element, linked to the member. Okay, and in this case xe is in the axis of the truss element, okay, and ye is perpendicular to it. So again, I have a force in the axis of my member and I have a displacement in the axis in the on the axis of my member, on my element, and certainly I will have displacement and force components which are perpendicular to it. So both are okay. I mean, you can write the relationship again. Of course, the static equilibrium will work, and sum of the forces in each direction has to be equal to 0. Now here is the trick. Now I write each of these forces and displacements again as a vector. Now I have 4 components for each element when I have 2 nodes. You see, I have my first node and I have my second node. You can group them in a different way. Here is, for example, one way of grouping. First, I write the forces of node 1, then in x and in y direction. Then I write the forces of node 2 in x and in y direction. In fact, you can do it in a different way. First, you can write the forces in x direction for both node 1 and node 2. Therefore, f2x will become the second member of this vector, and f1y will become the third member of this vector. One trick is you should follow the same ordering in writing the displacement vector. So this is the element displacement vector. As you see, first I have d1x here, then I have d1y here, then I have d2x and d2y. Okay, so let's see how I can write the stiffness matrices and the relationship between the stiffness matrix and the displacement vector. Now, of course, first I have an angle of rotation, okay? So I write the force equilibrium in xe prime and ye system. So I have this relationship from one-dimensional problems. Remember that. So ke minus ke u1 prime x. So this is u1 prime and this is u2 prime y. These are the rotated displacements, and then forces in these directions. Okay. And it is k minus k minus k k. Now in y direction I cannot write something because my stiffness, or in ye, okay, in ye, this is the coordinate system which is attached to the element. So in ye direction, forces has to be automatically 0, and I cannot write any relationship between the displacement in y direction or any displacement with the forces. So I cannot write any relationship. As a result, if I decompose this matrix and write it in an element-wise manner, because this is only written in along the x-axis, what I see is ke is the element stiffness which is given, or which we have calculated, then 1 minus 1, you see, because I want to write the relationship for the f1x, and f1x is nothing more than ke multiplied by u1x minus u2x, or u prime 1x u prime 2x, okay, minus, because of this one. Now I'm decomposing this. Now this line will give me the relationship between the displacements and f1y. Certainly all the members are 0. Now this line, the third line, will give me the relationship between the f2x prime with the nodal displacement. Now this is minus 1 here, so k multiplied by minus 1, and then k multiplied by 1, because only u1x, u prime 1x and u prime 2x will contribute to the f prime 2x. Now if I look at the f prime 2y, it has to be 0 because there is no relationship between the displacements and f2y, in fact. So this is how I form the element stiffness matrix. In fact, now I can write the relationship between the forces acting on the element and nodal displacement values in 2 dimensions. Now next is to use the rotation matrix. So we will rotate this system, and we will rotate this to the global coordinate system which we devised. This is our global coordinate system x and y, and ye and xe is the local coordinate system which is attached to the element. And we want to write everything in the global system also in an element-wise manner. Certainly we will use the geometry in this case, and u1 prime x is nothing more than u1x multiplied by cosine phi, so that's the angle, okay, plus u1y multiplied by sine phi e. So it's here. This angle is phi. Okay, so this is one thing. Now I write the u1x and u1y. Therefore I can write the rotated displacements by means of unrotated displacements, because I write the expression in rotated coordinates, right? xe and ye. So re multiplied by de will give me the unrotated displacements. So this is my displacements in the global coordinates, de, u1x, u1y, u2x, and u2y. So there is no prime there. Then my rotation matrix automatically becomes cosine this term, sine phi this term, minus sine phi this term, cosine phi this term. And this is for node 1. Certainly I can do the same for node 2. Okay. Now one property of the rotation matrix is it's orthogonal. So multiplication of one row which the other one will gives you 0 automatically, or multiplication of one column with the other one will give you 0. Therefore the inverse of this matrix, this rotation matrix, is equal to the transpose of it. this matrix also has another property. Multiplication of its transpose, certainly its inverse with itself, will give you the identity matrix. So it has such kind of a properties, and we may use it sometime later. Okay, now we have seen how to rotate the displacement. Now let's consider a fictitious system. Okay, any system with a given displacement, d bar e, and we will convert this into another frame, another coordinate system, and in that coordinate system our displacements are d with head. This is just an assumption. Okay, so I'm just creating a fictitious system. Now, therefore, I will have a transformation matrix T. It can be any matrix. It can be some matrix. So we don't know how the structure is. TE. And then we have our rotated system. Okay, so D prime is the matrix, D prime E is our rotated coordinates, and DE is our original one, and we rotate them, and then we obtain this matrix, this vector. Therefore, we can easily say that the transformation matrix is equal to the rotation matrix in our case. Okay, so okay, let's continue again. D prime E is analogous to the D hat, displacements in the headed coordinate system, and the displacements in the global coordinate system is analogous to the D bar, DE bar. Now let's write the work of internal forces. Okay, so small change, just assume that hypothetically I just make a very small displacement. Okay, so very small, the delta DE head, and the work done by this displacement is FE head multiplied by this delta DE head. So this is the work done. Okay, of course I can write the stiffness matrix in rotated or transformed coordinates as this. So TE transpose, this is T is the transformation matrix in an element wise manner. KE head is the stiffness matrix in the untransformed coordinates multiplied by the TE. So this forms my stiffness matrix in the global system. Okay, so this is how it works. Identically, I can write the force F bar as TE transpose multiplied by FE head. Now this tells me something. So when the matrix T is orthogonal, its transpose is identical or its transpose is equal to its inverse, right? And also we know something, be careful. Now this is the work, and work is a scalar quantity, therefore it has to be frame indifferent, which means that regardless of the coordinate system that I'm using, it has to be its value has to be the same. it shouldn't change. The value of the work shouldn't change with the change of the coordinate system. So delta DE hat, FE hat, has to be equal to the delta DE bar FE bar. Okay, now let's write the work again. So we know that force is equal to stiffness matrix multiplied by the displacement. Again, it is delta DE transpose multiplied by FE bar, and FE bar is equal to TE transpose multiplied by FE hat. Now, if I multiply delta DE, or if I write the work, because work has to be frame indifferent, and if I write the work in both frames and subtract them from each other, I will get this expression. So FE bar minus TE transpose multiplied by FE hat, and this has to be equal to 0. Now this tells me something. FE bar is equal to, so the forces in untransformed coordinates has to be equal to the transpose of the transformation matrix multiplied by the transposed coordinate system. Now I can write FE as KE hat multiplied by DE hat, as you see. Now this is what I have. TE transpose KE hat TE, and we know that this is K bar, and K bar is multiplied by the DE bar, this is FE. So as a result, by simply doing some algebra and using the frame indifference of the work, we can make the transformation from one coordinate system to the other coordinate system very easily, just by using the transformation matrix of the coordinate system. And in fact, in our case, this transformation matrix is nothing more than the rotation matrix. Okay, so let's consider a system with two members, and let's say that we have L here. L is they are simply supported at point 2 and point 1, and they are pinned at point 3. Now the coordinate system, the origin of the coordinate system attached to the node 2, and there exists a force of 10 applied to node 3. Of course, the distance between node 2 and node 1 is L as well. Now let's see, we have two elements, okay, and let's say that this is element 1 and this is element 2, and of course node 1 of element 1 is 1, node 2 of element 1 is 3, and it makes an angle of 90 degrees. Now for element 2, node 1 of element 2 is 2, and node 2 of element 2 is 3, and it makes 45 degrees. Okay, now let's calculate the transformation matrix first for the node for the element 1. Cosine 90 is 0, sine 90 is 1, so L1 is equal to L. So the K1 is area of element 1 Young modulus of element 1 divided by L1. So this is A, E divided by L. So as a result, the stiffness, element stiffness matrix is 0, 0, 0, 0, 0, 1, 0, minus 1, 0, 0, 0, 0, 0, minus 1, 0, 1. Or in other words, we have only y components in the direction of the element. Therefore, as you remember that the second and fourth rows are associated, columns are associated with the y coordinate components or components in y coordinates, and as a result the others are 0 and we have non-zero values in the second and fourth column or in the second and fourth row. Okay, now for the element 2, it makes an angle of 45 degrees and it is 1 over square root 2 or square root 2 divided by 2. So cosine 45. Sine 45 is also 1 over square root of 2. So L2 is square root L. And in fact, so this is the length of the element. K2 is area Young modulus divided by the length of the element, and which makes AE divided by square root of 2L. Now we can easily calculate the rotation matrix for this node. So we can substitute it into this matrix, and from here we can calculate the stiffness matrix as is the case in here. Okay, so RE transpose multiplied by K multiplied by RE. This will give us the stiffness matrix in the global coordinate system. And as a result, we obtain this matrix. Okay, so now we have the element stiffness matrices. Identically, we will sum up the values in each row and column. Therefore, 1, 1 will be summed with so this is the first and this is the second, so 1 and 3. So 3, 3 will be summed with the 3 3's here. So 0 will be summed with 1 over 2, 0 will be multiplied by 1 over 2, this 0 will be multiplied by summed with 1 over 2, and 1 plus 1 over 2. And as a result, if we do this operation for each member, okay, so we only have 1 3 3 3 1 1 2 2 2 3. This is what we are going to get. This will be your global stiffness matrix, in fact. Now these two rows are associated with the node 1, and these two rows are associated with the node 2, and these two rows are associated with the node 3, in fact. And certainly we have the global displacement vector. We know that node 1 and values, the displacement values at node 1 and node 2 are 0. So these are the values. And of course we have only force in node 3 and it's only in x direction. Certainly we have the reaction forces at node 1 and node 2 in x and y direction respectively. So we have 4 unknowns here and 2 unknowns here. We have 6 unknowns and we have 6 equations. And this is our global system of equations. So next thing is to solve this global system of equations. Okay, so what we are going to do is to decompose the system. First we will decompose the system into the essential ones. So the upper part, so the first 4 rows are due to the essential nodes. So this part basically from 1 to 1 to 4 to 4 is associated with the coupling between the essential nodes. This is the stiffness matrix of the essential part, and this part 2 to 2 system is due to the free nodes. Therefore we have the essential displacement vector here, dE bar. These are known. dF is a vector with 2 members. Then we have FF, so forces on free nodes 10 and 0. Now KF is a 2 by 2 matrix. RE is the reaction forces. It's a vector with 4 elements. Then we have the KEF, which couples the essential nodes with the free nodes. So it's a 4 by 2 matrix. Okay, so as a result, since the displacements in the essential nodes are 0, this is what we are going to obtain. So this is the system of equations for the free nodes. So we have a matrix, area multiplied by the Young modulus divided by L, 1 over 2 square root of 2, and 1 over 2 square root of 2 is the first column, and second column is 1 over 2 square root of 2, the second element of the second row is 1 plus 1 over 2 square root of 2 multiplied by the displacements of the free nodes. That's equal to the forces acting on these nodes. What we need to do is take the inverse of this matrix, and if we multiply it with the force matrix, what we are going to get is this. So U3x is equal to L divided by AE, and that is multiplied by 10 plus 20 square root of 2, and what we need to do is U3y. That's the next thing that we are going to find, and that is minus 10 AE. Now we have to find the reaction forces. Now reaction forces is equal to KE multiplied by DE. DE are the known displacements, DE bar. Now we have calculated the DF. We know since KE multiplied by DE bar is 0, we only need to do this operation, KEF multiplied by DF. And KEF is this 4 by 2 matrix. And if we multiply this matrix with this vector, basically we will obtain the reaction forces. 0, 0 multiplied by these values will give us 0. 0 minus 1 will give us 10. And it goes like this. So each row will be multiplied by this vector, and we have 10, minus 10, and minus 10 for the components of the reaction forces. So certainly R1x is 0, R1y is 10, and R2x is minus 10, and R2y is minus 10. So it comes from the static equilibrium conditions, so therefore they satisfy these conditions. So remember that these are my forces, and this is my R1y. R1y is summed with R2y, and that gives 0. And I have minus 10 here for the R2x, but remember that I have an external force of 10 acting on the system, and as a result sum of the external force 10 with minus 10 will give me 0 as well. Of course you can easily check that M2 is 0, so taking the moment will be satisfied automatically.